welcome you to our third class. Here we're going to be looking at a simple example again to further deepen our understanding about the application of the per unit representation in solving power system problems. Here we have also a power system represented using a single line diagram. We have a generator, we have a transformer, we have another transformer. This transformer is stepping up the voltage that is coming in. The voltage coming in is 10 kilovolts. It steps it up to 20 kilovolts. The voltage gets to this transformer steps it down further to 10 kilovolts. So we are required to find the per unit value for each component and to draw the per unit equivalent circuit. I believe by now you should have been very conversant with how to draw the per unit equivalent circuit and actually how to find the per unit value. Find the load current, actual current in every component, and voltage drop in every component if the load voltage is 1 pu. We are also asked to determine the per unit generated voltage and the actual generated voltage. Before we get into solving this problem, it is very important to still remember the procedures involved in solving the power system problem using the per unit representation. First, we are asked, you need to get your base power. You need to also find your base voltage, and like we said earlier, the base voltages would always change if there are transformers. And if you take note, you see that this system will have transformers. So the base voltage here would be this 10 kV for instance, but when it gets to this place it will change because of this transformer. When it gets to this point also it will change because of this transformer. Then having gotten that, then we'll get the base impedances, for each of the region. As the voltage changes, the base impedance also changes, but we have maintained that the power remains the same. So we look for the base impedances of each of those sections. Then if we have our actual impedance, we will use our actual impedance value, compare it with the base impedance so that we can find our per unit value. So now let's get into solving this. So like we said, first your base power. So like we actually informed you, the base power can be assumed to be the power of the biggest generator in the power system. We can also decide to take the voltage of that same generator, which is from what we have. Can we go back to it and see? You can see here that this generator, the voltage is 10 kV, whereas its power is what? 100 MVA, and we are taking its value as our base values. So you can see for that we have 100 MVA as a base power, and we have the voltage, base voltage, as 10 kV. But this 10 kV is actually in region 1. Now region 2, which is due to the transformer, transforms this 10 kV into 20 kV. Now we also have the second transformer, which divides the power system. It transforms finally this 20 kV coming in, it transforms it into 10 kV. So having found the base voltage of the three sections, the next step becomes to look for what? The base impedance in the three regions. So we see the base impedance for region 1. Already we know this formula, that is ZB1, which is equal to V squared, the square of the voltage in region 1, the base voltage in region 1, all over the base power. We know that the base power remains the same for all the regions, and there we have 1 ohm. We do the same thing for region 2, and we have 4 ohms. The same thing for region 3, and we have 1 ohm. Now you see the next step is to find the per unit impedance for each of the components in each region. So first and foremost, we remember that in region 1 we had our generator. Generator is in region 1, so when we consider the generator in region 1, so we look at what's the base impedance for region 1. From our calculation, we got that our region 1, the base impedance was 1. So this is the actual impedance of the transformer. If you refer back to our diagram or the power system network, you will see that this is the actual impedance given for the generator. So when we divide that, this will arrive at our per unit value. Then we go to transformer T1. We are considering its primary side, which is actually also in region 1. Yes, if we consider the primary side, which is actually in region 1, so were we given the primary side impedance? Of course, we are given the primary side impedance. It is important to note. Let's go back to that sketch. Now look at this. Look at. You will see this statement made here. He said, this is the impedance of the transformer referred to the 10 kV side. Where is the 10 kV side? This is the 10 kV side, which is actually the primary side of the transformer. So it then means its per unit value, like we did in our initial example. If you remember the first example we did when we were trying to show you that whichever side you refer, that your per unit's value remains the same. So you remember, now we have that this impedance is on the primary side of the transformer, which means we are going to be comparing it with what? The impedance in this region. And we told you that this is region 1. Look at also for this transformer. Where is it referred to? It says refer to the 10 kV side. Where is the 10 kV side? This is actually 20 kV. This side is the 10 kV side, which is the secondary side. And this region is in the region 3. So when we'll be looking for the per unit value of this transformer here, we'll be considering the base impedance in region 3, so that we can determine the per unit impedance of this transformer. So let's go back to where we were. Now you can see when we get back here, now we're dealing with T1. Now T1, we told you, because the impedance was referred to the primary side, so we take what's the base impedance for the primary side, which is region 1, is actually 1. So we apply that with the formula we have, and at the end of the day, this will be our per unit value. Then we move straight, because there are no other components in region 1, we move straight to region 2. The transmission line is in region 2. So when we take the transmission line, we also go back to look for its per unit value. So look at the per unit value is also the actual impedance of the transmission line all over ZB2, because it is in region 2. And this is the actual value given for the transmission line, and this is the base value in region 2. So at the end of the day, this is what we're going to have in per units. Good. So now region 3. Now when we get to region 3, what do we have in region 3? Remember, like we said initially, that this transformer, we were given its impedance referred to the 10 kV side, which is actually the secondary side. So finally, we are going to be considering this transformer 2 in region 3. So when we compare that to find its per unit impedance, we're going to be using its actual impedance, which has been referred to the 10 kV side, with also what is the base impedance of that 10 kV side, or the region 3. What did we get as our base impedance? Our base impedance for region 3, if you go back to our calculation, our base impedance for region 3 is 1. So when you compare that, this will be our per unit value. Then remember that the load is also in region 3. So when we do that for the load, the actual impedance of the load all over the base impedance of region 3, where the load is actually located. And this is the actual impedance. This is the base impedance in region 3, which is 1. So at the end of the day, this is our per unit value. Having done that, we are now ready for the equivalent circuit. So you can see the equivalent circuit, which contains all the per unit values that we calculated. So this is the generator in the system. This is its per unit impedance. As we get here, this is transformer T1, and this is its per unit impedance. This is the transmission line, and this is is per unit impedance. This is ZT2, the transformer 2. This is is per unit impedance, and this is the load and is per unit impedance. Now we have dealt with one stage of the problem. Now, what is the second stage? Let's move. Now, the B part of the question says determine the load current, actual current in every component, and voltage drop in every component if the load voltage is 1 pu. So we have been told that the load voltage is 1 per unit. Wow. So if we know the load voltage, which is 1 per unit, we can calculate the load current. Of course, we can determine the load current using Ohm's law. And this is it. I is equal to V all over Z. Of course, you know that Ohm's law states that V is equal to IR. In this time, we are dealing with AC network where impedance is considered instead of resistance. So we'll be looking at V being equal to IZ, and make I the subject. I becomes V all over Z, and that's it. And what is our V per unit? That is our voltage in per unit. It is 1.0 like we have here. Then what is our the per unit impedance of the load? This is it. And when we do that, at the end of the day, this will be our solution. Now let me take you back here. If we have that our IPU, or current in per unit for the load, is this, let's look at this circuit. You can see from here that whatever current that is coming into here, because all these things are connected in what? In series. So whatever current that is coming in here is equivalent to the current here, is equivalent to the current here, is equivalent to the per unit current here, is equivalent to the per unit current here. So having gotten this current, you know, with that we can determine the voltage drop here, which should be I times Z, the voltage drop here, which will be I times Z, the voltage drop here, which is also I per unit times Z, and with the same case here, we can get the voltage drop for all of them. So let's proceed. So now we are asked to find. Now we have already explained this. Notice from the circuit that IPU per unit load is equal to per unit line is equal to per unit generator. So we have that, but base current value at each component is, so we want to find the base current value at each component. Now why do we need to calculate that? Because mind you, we're asked to determine the load current. After determining the load current, then we say actual current in every component. So having gotten the load current, now we can determine the actual current in all the components, because the load currents like we have in per unit is equal because the entire component are connected in series. And then all we need now is to find their base current. Now remember that we know from the first formulas that we gave to you that the per unit current is equal to the actual current all over the base current. So now what are we going to do here? Well, for us to get the actual current, we need the base current because we already have the per unit current. So how do we calculate the base current? Remember the formulas we gave to you for base current in a three-phase system, where we say I base load is equal to that all over root L base. So we know our base voltage for region 1, which is region 3, where we have the load. So the load voltage there is 10 kV. So we know the power is 100 MVA. So this is the base current. So also the base current for the line. What is the base current for the line? Of course, we know that the line voltage is 20 kV. Then we'll put that into this formula finally, and this is what we have. Then the base current for the generator, we know the generator voltage is 10 kV, its power is 100 MVA. I mean the base power is 100 MVA. So, and we have this. While this is the base power, base voltage, base power, base voltage, please do not forget that. So now, therefore, the actual current value at each component is, now because we have gotten the base values, so we can now determine the actual current in each of those components. So like we have here, if you look at that, we see that the I load, this is the actual current for the load, is equal to the I base load times I per unit load. So at the end of the day, this is what you're going to have. The same is applicable to the line, I baseline, I per unit load. Mind you, we are just retaining this load because I load and I line, I per unit load and I per unit line, they are the same. We told you they are all connected in series, so we are repeating them just the same way. So we have I generator is equal to I base generator time IPU load, and that's what you have. Then now the voltage drop at each component. Yes, of course, having gotten that, we can determine the voltage drop at each component. How can we find the voltage drop at each component? Simple. This is the per unit voltage drop. So the per unit load current times the per unit impedance of the generator will get the voltage drop across the generator. What about across transformer 1? We have the per unit current, yes, passing through the transformer, which is also the same thing as the per unit load current multiplied by the impedance in per unit of transformer 1, and that is that, and you have this as a solution. Then you do the same thing for the transmission line, because yes, you run that and you have for the transmission line, you have that the I per unit load, which is like we said, maintaining the same explanation, that IPU load is equal to I transmission transmission line per unit. So you see, multiply by the impedance in per unit of the line, and you have that. The same case for the transformer 2, which is also part of the circuit for the transformer 2. We still maintain IPU load time ZPU transformer 2, that is the impedance of transformer 2. And when you do that, you have this as a solution. Then in this case, finally, we have been able to get the per unit value of the voltage drops across all the components. Then now C says determine the per unit generated voltage and actual generated voltage. Now we were asked to determine the per unit generated voltage. Of course, you know the generator is what is supplying the load, what is supplying the line, what is supplying the transformer. So the drop on the line plus the drop in the two transformers plus the drop in the load plus also the drop due to the internal impedance of the generator. Just like we have, I'll take you back to the diagram. So look at this figure again. So what the voltage generated by this generator will be the voltage drop here plus 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 the voltage drop here, all added together will sum up to give you the voltage generated from this source. So let's go back. Now you can see that here. So we have that this is the load in per unit, this is VT2 in per unit, this is VTLPU in per unit, this is VT1 in per unit, then finally VGPU, that is the voltage drop due to the per unit impedance of the generator. Then now we look at that. So actually we have calculated all these things. We were told initially that VLPU, that is the voltage on the load voltage, is actually 1 pu, so we are returning that 1 pu. So plus VTUPU, we have already calculated all of this. You can see VTUPU. Where is VTUPU? So look at it, VTU1. So you can see that. So this is that. Yes, the voltage drop across transformer 2, the voltage drop across that. So we have all of them added. When you add all the voltage drop that were calculated, this is what it will give you at the end of the day. Like we said, we have calculated all the voltage drop, just add them together and you will have this. So having gotten that, you will get your voltage drop in per unit. But of course, we are asked to also find the per unit value and find the actual value. So how do we get the actual value? We just multiply the having gotten the per unit value. What is the base value of the region where we have the generator? Mind you, we took the base voltage of the generator as our operating base. So we can simply just bring out the base value of the generator multiplied by the per unit value so that we can get the actual generated voltage. And finally, this is what we have: 21.2 angle 26.5 degrees kilovolts. Wow. So finally, we have come to the end of every example that we need to solve in terms of the per unit. So this is a simple problem for you to get to try your hand on, see what you can do, what you're going to get at the end of the day. You are asked to find, you are given the figure, and we are asked to find the current supplied by the generator, transmission line current, the load current, the load voltage, and the power consumed by the load. Choose a base MVA. We are giving you base MVA of 100 MVA and 138 kilovolts at the line. It's important for you to note here, when you look at this problem, where do you have the 138 kilovolts? Yes, where do you have? This is 11.2 slash 132. So you can see this is where you have the 138. That was what was taken. So mind you, if you are bringing it here, that 138 is a large voltage. You don't assume that 138 will go in. No, when you are now working here, you're going to be bringing this 138 because this is where it is. So 138, you will transform it to get what the value is going to be here. You transform the 138 also to get what the value is going to be here. So what it means is that the transmission line voltage was actually taken as the base voltage, which is what? 138. So we take the voltage here, 138, as our what? Our base voltage. Very important. So let's not forget that and try to solve this problem. Now this is a solution that we have at the end of the day. This is the solution to the problem. These are the answers, so you can give that a try and see what you get out of the day. I hope you have learned a few things from these examples that we have shared with you so far in this course in per units. I hope you will still go and try these assignments for yourself and get to improve your hand. Thank you for listening.